Hi, welcome to another Algebra 1 video. In this video we're looking at section 3.7, Absolute Value Functions, Part 1. In this video we will learn about the parent function of all absolute value functions, and we will also look at some general graphing of absolute value functions through table sets. So before we talk about what the parent function of all absolute value functions is, let's first talk about what the absolute value term even means. In the simplest definition from middle school, you may have learned that the absolute value of any number is its distance from 0. You may also know that you can put the absolute value between two bars and you place an x in between, and that x consists of all numbers in the real number line. So here I have some examples of absolute value expressions. You could, for example, take the absolute value of the number 6. So 6 is 6 units away from 0, so the absolute value of 6 would equal to 6. Another way you can think about absolute values from the negative side of the numbers. So if you take the absolute value of -1, then the distance that -1 is from 0 is +1. You could also take the absolute value of 10,001. How far is 10,001 from 0? Well, it's 10,001 units from 0, so your absolute value of 10,001 would be the same as 10,001. But how can you characterize the absolute value expression in a function? How would you see it in a function? We know that you can write the absolute value expression with an x in between, and you can set it equal to y so that you have some function now. Now that you have y, which is your dependent variable, and the x in the absolute value terms, your independent variable, you have created a parent function for the absolute value functions. But what exactly is a parent function? If you've been looking at my previous videos on linear functions, you'd know that the parent function for any function is the simplest form of a function that you can have. So in this case, when we look at absolute value functions, your simplest form of the function will be y equals to the absolute value of x. Now the reason why it's the simplest function is because we're not applying any transformations on it. You would know by now that transformations are operations on the original parent function, which make a derived function of the parent function. So when we talked about linear equations, we knew that the parent function for all linear equations was represented by y equals to x. And we knew that you could transform this function by adding stuff, multiplying stuff to x, or reflecting it across axes. Well, you can do that to linear functions by multiplying stuff, for example. So if you multiply -1 to x, then you're reflecting it across the x-axis. Similarly, you can transform it by adding some factor, say -6, for your h value, or you could add another number on the end of this function, for example +7. Then this 7 is your k value from transformations, which determines by how much your function is being shifted upwards. And last of all, you could also multiply the x by some coefficient of, say, -2. So here I have y equals to -2x, and in this case I'm not only reflecting it across the x-axis because of that -1, I'm also doing a vertical stretch by a factor of 2 because of that 2 coefficient on the x. So all of these functions that are written over here are all just derived or transformed functions of the original function y equals to x. Now if we look at absolute value functions, we know that the parent function is y equals to the absolute value of x. We can transform this function in similar ways just like linear equations, as I've done over here. So let's transform this function to produce different functions. You could come up with y equals to negative times the absolute value of x, and this transformation would make it reflect across the x-axis. You could come up with y equals to negative times 2x, and what this function will do is shrink it horizontally by a factor of 1/2. Or you could come up with another function, say y equals to negative times the absolute value of x plus 7 on the outside. In this function you're doing a reflection across the x-axis because of that -1, and you're adding 7 to the function, so that transforms the function in a translation transformation by shifting it upwards by 7. So the key thing to get from all of these functions is that you can transform the parent function y equals to the absolute value of x in different ways, just like how I transformed the linear function y equals to x. Now that we know what the parent function of all absolute value functions are, let's look at how graphing absolute value functions works in terms of table sets. So here I have my coordinate plane and the table set in the x and y values. So let's graph the parent function y equals to the absolute value of x. So I've placed the x values for which we will be graphing this function for the respective y values that we will get. So I'm graphing this function for -3, -2, -1, 0, 1, 2, and 3 for our x values. And let's find the y values for all of these x values, and then we will graph them on the coordinate plane. So what is the absolute value of -3 when we plug it in for x over here? Well, negative 3 is a distance of 3 from 0, so our absolute value of negative 3 will give us 3. Now let's graph that point on this coordinate plane. So our point is negative 3, 3, so negative 3 along the x-axis, and up to 3 on the y-axis. So our point is going to be there. Now our second point is negative 2 for x. So when we plug in negative 2 for the absolute value of negative 2 is a distance of 2 from 0, so our absolute value of negative 2 will equate to 2. And let's plot this point on the coordinate plane. So negative 2 along the x-axis over here, and then 2 along the y-axis will put our point over here. Our third x-coordinate is negative 1. So when we plug in negative 1 for our x value, what is the absolute value of negative 1? Well, negative 1 is a distance of 1 from 0, so our absolute value of negative 1 will equal to positive 1. And when we put that on the coordinate plane, our point will be negative 1, 1. So our point is here, negative 1 plus 1 along the y-axis. And then our fourth coordinate for x is 0. What is the absolute value of 0? Well, 0 is the absolute value of itself because 0 is a distance of 0 from 0. So the absolute value of 0 will equal to 0. And the point 0, 0 is of course at the origin, so we'll place that point over here. Our fifth x-coordinate is positive 1. What happens when we take the absolute value of positive 1 in the absolute value function? Well, 1 is a distance of 1 from 0, so the absolute value of 1 will also be 1. And the point 1, 1 will be over here. Now for the second last point, what is the absolute value of 2 when you plug it into the function? Well, the absolute value of 2 means 2 is a distance of 2 from 0, so the absolute value of 2 is also going to be 2. So the point 2, 2 will be over here. And finally, what is the absolute value of positive 3? Well, when we take the absolute value and we plug in the 3 into the absolute value function, we get that the absolute value of 3 is equal to positive 3. So when we graph the point 3, 3, it lies over here. So you can already see the pattern between the points is starting to look like a V. Anyways, let's connect the dots and see what the graph looks like, and then we'll analyze some of the properties. So we can see that the graph in the red line looks like a V, and this is a property for all absolute value functions. We can see that the function y equals to the absolute value of x has an x-intercept and a y-intercept that is shared at 0, 0. We can see that it also has a constant change in its x values as they move to the right, and it's also constant as they increase upwards along the y. So if we take the slope of this function on the right side of the y-axis, then we'd know that the change in y over the change in x is equal to positive 1 over positive 1, which means that the slope is equal to 1. However, if we look on the left side of the y-axis, we can see that we move backwards by a value of negative 1, but then we move upwards by a value of 1 to reach the point negative 1, 1. So if we take the slope of this line over here on the left of the y-axis, then our change in y over the change in x will equal to the change in y, which is positive 1, over the change in x, which is negative 1 because we're moving backwards, and our slope overall will simplify to negative 1. So what this tells us is that the slope of this graph is not the same everywhere. The slope of this graph is negative in the beginning, but then it moves upwards and the slope becomes positive. So we can say that the magnitude of the slopes is the same. However, the direction of the slopes is reversed because here we have that negative sign, but over here it's positive. Now let's analyze how this graph is different from the graph of a linear function. We already know by now multiple times that the parent function for linear functions is y equals to x. And we also know that the parent function is a simple line and it's not like a V graph like this absolute value function. So if we were to graph the parent function y equals to x for all linear functions, then we would get a line that exceeds downwards and the slope does not change. So if we plot the points behind the y-axis for the parent function y equals to x, we would notice that the points of the parent function y equals to x are negative instead of positive like the parent function y equals to the absolute value of x. And we can see that because this over here is positive 1 while over here it's negative 1. So we have a reflection that's going on behind the y-axis. Similarly, for the second pair of points behind the y-axis, we can see that this point negative 2, 2 is a reflection of the point over here negative 2, negative 2. So these points are reflections of each other. And similarly, we can also say that the point negative 3, positive 3 is a reflection of the point negative 3, negative 3 from y equals to x. Finally, we can also note that the slope of the parent function y equals to x is different from the parent function y equals to the absolute value of x behind the y-axis. So if we take the slope of this function behind the y-axis, we can see that we're going down our change in y is -1, but then we're also moving backwards by -1 on the y equals to x function. So what this tells us about the slope of the function is that the change in y over the change in x is equal to -1 over -1, which is equal to +1. And we can see that the slope behind the y-axis for the parent function y equals to x is the same as the slope after the y-axis for the parent function y equals to the absolute value of x. And this also tells us that the parent function y equals to x has the same slope for all x values, unlike the parent function y equals to the absolute value of x. And this is it for section 3.7 part 1. Leave a like if you found this video helpful and subscribe for more videos in the future. And I'll see you in the next video. Thanks for watching.